In homework 8.3, we're dealing with transforming log parent functions. So we're going to use some of our log knowledge, and we're also going to use some of our knowledge of transformations to be able to do these problems. Let's look at number 2. It asks you to start by writing the equation of a logarithm with a base of e, which is of course a number, that's shifted right by 3 and down by 2. Now we don't write log base e. When it's log base e, it's the natural log. So I'm going to write the equation y equals the natural log ln of, the parent function would be natural log of x. And I'm going to take a second just to graph that in red over here to make sure we know how to graph a logarithm. All log parent functions have an asymptote at x equals 0. And they have a point at 1, 0. They follow the asymptote here. And then there's an easy second point we can do, which is whatever the base of the log is, which in this case is e. So we do need to know that e is about 2.7. So 1, 2.7. Log base e of e would be 1. And so that's our nice second point we can get. Now that's good enough for log base e. For some other ones, we might be able to do more points, but for log base e, the natural log, that's all we're going to do. Okay, so here's this function, and we're going to be shifting it right by 3 and down by 2. So this is where our knowledge of transformations comes in. The natural log of x is going to be shifted right by 3, and so we're going to put x minus 3 inside parentheses, inside the function. And then to shift it down by 2, we're going to subtract 2. When we shift it right by 3, the new asymptote, everything's going to move to the right by 3, and so this asymptote, instead of being at x equals 0, is going to be at x equals 3. So the old asymptote was at x equals 0. The new asymptote is going to be at x equals 3. I'm going to go ahead and graph the whole, it says to graph it, so we should graph this, set it up at the top. And so I'm going to graph, this point is going to shift, I'm going to take this point at 1, 0 and shift it 1, 2, 3 to the right and 2 down. And I'm going to take this point at e comma 1 and shift it 1, 2, 3 to the right and 2 down. Notice that it's still not on a lattice point, it's not on an exact point. And now I can follow the asymptote, and this is good enough. All right, so here's my log graph. The asymptote we can see is at x equals 3. The domain is all the values to the right of 3. So we can say x is greater than 3, or we could say 3 comma infinity. This is the interval notation. The range for all logarithmic functions, the y values, it'll keep going down to infinity. And even though it's growing slower and slower and slower, it will reach all values eventually. So all real numbers, or all values between negative infinity and infinity. The end behavior. This is something that should be fairly new to us, but it's something that we want to get better and better at as we get to higher level math. The end behavior is talking about these two ends. Okay, and I'm going to start with this end first, the end on the right. The way we say end behaviors is using limits. The limit, LIM we use for short for limits, the limit as x goes towards, this end is going towards infinity. As x goes towards infinity of natural log of x minus 3 minus 2. Now, I'm going to tell you a nice shortcut, is if we had called this f of x equals instead of y equals, in our limit, we could have just put limit as x goes to infinity of f of x, and it would have saved us some time. It's a good reason not to use y equals and to name your function. Okay, this limit, as x goes towards infinity, the y value is going to go up and up and up and up and up, and it will go towards infinity. Or we can say that this limit does not exist. There is no limiting value. The y values just keep growing and growing and growing. The other end is the limit as x goes towards, this x is not going to pass the asymptote. And so we say as x goes towards 3, and if we want to be really fancy, we can say as x goes towards 3 from the right side. This plus means we're coming in from the right side. We're going to be a little bit bigger than 3. So limit as x approaches 3. And now that I've named it f of x, I'm just going to put the limit as x goes to 3 of f of x. And as x is getting closer and closer to 3, the y values are going down and down and down, and those are going towards negative infinity, which also, that limit doesn't exist because there is no limiting value, we would say. Okay, well, hopefully that helps. Oh, increasing or decreasing. We read from left to right, and as we read from left to right, this function is going up, we say it's increasing. as we read from left to right, even though it's increasing, the function is bending down. If it were a straight line, it would look kind of like this, but it bends. I hope you guys can see it's like bending down. And so we say it's concave down because that's the way it's bending. It's bending downwards. Okay. On the back, oops, what did I do with the back? It's somewhere for you. Hold on. It fell off the table. All right. On the back, I'll do a few of these with you. I think I'll do number 4. What is the base of this logarithm? Well, it doesn't say the base, and we should know from logarithms that if it doesn't say the base and it says log, that means the base is 10. F of 100 means we're doing log of, we're putting in 100 for x. So log of 10,000 times x, which is 100. This is log of, when we multiply numbers with zeros, we just add up the number of zeros, so it's 6 zeros total. And this question is asking us to say 10 to what power gets us a million? So how many 10s do we need to multiply together to get a million? That's 6. So f of 100 is 6. It says without using a calculator, estimate the y value when x is 4. Get log of, when x is 4, we're going to put in 4 for x, so it's 10,000 times 4. I'm not going to write it out again, it's just 40,000, sorry. And we need to estimate this. And so our estimation skills, we're going to say, well, 10 to the 4th power would be 10,000. That's too small. 10 to the 5th power is 100,000, and that's too big. And so it's somewhere in between 4 and 5. This is asking us what exponent do we need to put on 10 to get to 40,000, and because the exponent 4 would be too small and the exponent 5 would get us an answer that's too big, the answer's like, I don't know, 4.5, 4.6, I don't know. Something like that. This is an approximation. We can use a curvy equal sign. That means approximately equal to. And, you know, if we wanted to, we could have done this another way. There's a cool trick we could do with tens, which is we could say this is 4 times 10,000, which is what it was to begin with. And we can use properties of logs to split this up. This is log base 10 of 4 plus log base 10 of 10,000. And this one is equal to 4, and then this one is equal to, okay, log base 10 of 1 would be 0. Log base 10 of 10 would be 1, so this is somewhere between 0 and 1. And again, if we add a number between 0 and 1 and 4, we'll get, 4 point something. Okay. What is the transformation of this? So what is this doing? Well, remember it's inside of it and it's multiplying. And so when we multiply a number inside, this is a horizontal compression. It's backwards from what you would think it would be. It's not horizontally stretched, it's horizontally compressed by a factor of 1 over 10,000. Tricky thing. So each x value is going to be 1,000th as far as it needed to, 10,000th as far as it needed to be. Now, this didn't get shifted to the left or right, and that's the only thing that's going to change the asymptote. So since it didn't get shifted to the left or right, it still has an asymptote of x equals 0, just like the parent function. It asks us to use properties of logs. And so for this, we're going to use the fact that 10,000x means 10,000 times x. And when two logs are multiplying, we're going to say this is log of 10,000 plus log of x. We can simplify this. So this is what f of x is equal to. Log of 10,000 is saying 10 to what power gets us 10,000? 10 to the 4th power gets us 10,000. And so we get 4 plus log of x. So what new transformation can we tell from this? Well, this is shifted up by 4. This could be rewritten as log of x plus 4, which is a shift up by 4. So shift up by 4. What are two easy points we can find? Well, actually I'm going to use this one. I find this version easier to use than this. I know that this is a log parent function, which makes it easier to find easy points. I know the log parent function would have the point 1, 0 on it. And if that gets shifted up by 4, the y value will change. It'll add 4 to the y value. And so one easy value is 1, 4. The other easy value from this parent function would be, because the base is 10, when x is 10, log base 10 of 10 would be 1. And if we shift this up by 4, well, now we'll have 10 comma 5. So that's it. That's all I'm going to do for helping on this. There are some cool like little things going on in the rest of it. Hopefully that was a help.